Hello everyone, I'm Sadia and I'm here to present my work on hyperspectral super resolution via denoising diffusion models. This is the overview of my work. I'll talk about the background, the challenge incurred in the work, the motivation behind using diffusion models, methods, finally the results and our future work. First of all, we ask ourselves, why do we need hyperspectral data and why do we even need its super resolution? Hyperspectral data is used for collection across entire range of electromagnetic spectrum, unlike humans which can only collect and process data across the visible range. But this data is compromised because of the limitation of incident energy, and because of that there are a trade-off between the spatial and spectral resolution in the hyperspectral data. But there are two different types of hyperspectral data which we can see in which we can handle the data, which is one is single image super resolution and another is fusion based image super resolution. So fusion based super resolution um, causes auxiliary information to be used with the image, but single image super resolution, quite frankly speaking, is very straightforward and is quite flexible. So that's why it's been used over fusion based image super resolution. But this imaging super resolution has received less attention because there has been little advancement, and also we do not have additional auxiliary information in single image super resolution. But with great deep neural network techniques and convolutional neural networks break in the modern science, we see that deep CNN has shown extraordinary capability of modeling relationship between low resolution and high resolution images. But we see that hyperspectral data is not without its challenge. It is increasingly difficult to create an effective and efficient environment, and that is because of the popularity of hyperspectral images. Hyperspectral images require a lot of imaging samples to be trained, but because of instances, say, because of difficult camera, different camera sensors in difficult situations, we often get different image sets from the same scene, and hence this also causes differences in number of spectral bands and imaging conditions. Plus, spectral dimensionality of hyperspectral data is quite high, which leads to these challenges. So the motivation is clear to work in this area. We we are thinking of using the property of spectral correlation among bands, and because of that we come up with a spectral grouping mechanism which exploits the correlation structure of hyperspectral image. Diffusion models are are the newest models which capture more abundant features. They also take advantage of extra and unique dimension of the time step. It's their main advantage. It constructs data generation process through iterative denoising. So this is our method. In forward process, we have a hyperspectral cube. We go for spectral reconstruction and we divide the D equal to 31 bands into these three different types of bands based on spectral response function. After that, we concatenate the features from each group and send them to a particular hyperspectral imaging patch. After that, in denoising models, we use a conditioning. That is, we use the interpolation technique in conditioning because we want to see how the reconstruction process looks. And because of this conditioning method, we see that We use three different types of units, and these three different types of units, then in the reverse process, are again concatenated to form a full-sized image back. So this is the architecture of hyperspectral reconstruction via denoising diffusion models. So these are the results that we have obtained. This is the ground truth of one of the data sets that we've used, ground truth image. And let's see how closely our image fits to this ground truth image. This is the reconstructed image of the same image. It's very hard to tell the difference between the two. And this is the diffusion, entire diffusion process. It starts with a low resolution image, and then it denoises it across varied time steps till it gets the high resolution image back. This is another example of our work. So this is another image from the same data set, entire 2022. And as you can see, there is hardly any difference between the two. It has learned the details, it has learned intricacies, learned texture, um, and this is the diffusion process, how it learns through the steps. But since this work is in progress, we also report some noisy reconstructions. This is our the ground truth from the same data set with the same learning, and these are the reconstructed images, and this is how the diffusion process looks. The model is able to learn every detail, but it's not been able to denoise it properly. One another example from the noisy reconstruction is these different colors that you see is the band information across different across this image, and we see that how noisy this image has turned out to be. Although learning every other detail in the image, it's not been able to denoise it properly, and this is how it looks. With that, I conclude my presentation. Thank you for listening.